Today we'll be working on the following problem. Suppose that the set of all positive real numbers R plus is partitioned into two disjoint sets, E1 and E2, each of which is closed under addition. So which means like for all x, y in E sub I, x plus y is also in E sub I equals 1 or 2. So we want to show that both E1 and E2 are not Lebesgue measurable. So pause the video if you want to work on this problem by yourself. Okay, so let's give a proof. Basically, we know like from last session, we know such partition exists if we assume axiom of choice or equivalently Zorn's lemma. So we know this partition exists. We want to show whether it's not Lebesgue measurable, which is not a surprise because the existence of a Lebesgue measurable set is equivalent to you are assuming the axiom of choice or the Zorn's lemma, right? So here, let's recall the we're going to use the conclusion from problem 7. So basically it says if a measure of a set, Lebesgue measure is greater than 0, then this set E plus E contains an open interval. So let's see how we use this. So assuming we're going to prove it by contradiction. Assuming that E1 and E2 are Lebesgue measurable, we want to reach a contradiction, right? So because they are disjoint and the union is the real positive real numbers, and then so both of them, either both of them are Lebesgue measurable or none of them are Lebesgue measurable, right? So if we assume they are measurable, now there are like from last session we also know like if this written into the union of E sub 1, E sub 2. Let's assume 1 is in sub 1. So from last problem, like we know this positive rational numbers are subset of E, right? So you can go back to that problem to see the argument. So which means like E2 is a subset of irrationals, right? Okay, so if we assume like they are both Lebesgue measurable, so the case is like we can have either, if this measure is great, either it's 0 or non-zero. So if we assume the measure of E sub 2 is greater than 0, then by applying the problem 7, we know this E2 plus E2 is a subset of E2, right? Because E2 is closed under addition, but E2 plus E2 contains an open interval. So there exists an open interval which is in E2 plus E2, right? Which is in E2. But in this open interval, we can always find an irrational, a rational number. There exists rational number R in this open interval. So then we have R is in E2, right? But we already said E2 is a subset of irrationals, so this is impossible. this is impossible. So the second case is like if this equal to 0, the measure equal to 0, but then we must have this the Lebesgue measure of E1 is greater than 0, right? Because the the measure of R plus is infinity. So in this case, we also use the same argument. So we can have a open interval is a subset of E1 plus E2, E1 plus E1, which is also a subset of E1 because E1 is closed under addition, right? So in this case, because since E2 is not empty, right? So we can find some R in E2. We can find some R in E2, right? So now consider this. We have, consider this now, this interval, from R over B to R over A. This one contains a rational, right? So because rational numbers are dense, so contains a rational, let's see, M over N, right? So basically we have R over B is less or equal than M over N, less or equal than R over A, right? So if we rewrite this, what do we have? We have this, multiplied by N and M. We rewrite this, it's gonna be like N times R is less than M times B, but bigger than M times A, right? So this means this N times R in the open interval from MA to MB, right? But since E1, we know this open interval A comma B is in E1. So if you keep adding M times, this will be in E1, right? So this open interval is in E1. But you add R n times, so it will be, because R is in E2, so this one is also in E2, a contradiction. All right, so by this two case, we conclude that E1 and E2 are not measurable. That's it.